Today we're going to take a look at section 1.10, which is radical expressions. And I want you to recall that when you talk about a square root that's a perfect square root, which we did back in section 1.1, that something like square root of 25 is equal to 5. And the best thing we could do back in section 1 when we talked about square root of 50 is sort of approximate what it had to be between. So we looked at something that would be a perfect square slightly less, a perfect square slightly more, and said, hey, the number should be in between those as an approximation, and that's the best we could do. Remember that? Yeah, great. So what we're going to do next is we're going to actually simplify them exactly, at least as far as they're able to be simplified. So we won't have a whole number coming out of them like we do for square root of 25. And we won't have a decimal approximation either, but we will have a different version of the value that's simplified. Let me do this one. Well, actually, our first example is the same here. So number 1. So square root of 50, what we're going to do is we're going to break it down into its factors. Oops, let me get a black pen back up. So for example, and I'm going to show it to you in a very specific way because it's going to move along into numbers part 3 and part 4, question 3 and 4 here better than other options. So we're going to break it down into its primes. So one thing you might do is you might say that this is 2 and 25. 2 is prime. 25 is not, so we would break it down again into 5 and 5. Those are all primes now. So I'm going to rewrite this as the square root of 2 times 5 times 5. So pretty good so far. You should be able to go backwards. You should be able to multiply those 3 together and get back to 50 if you've factored it correctly. Okay. Because this is a square root, and some of you are like, well, of course it's a square root. What else would it be? Well, actually, there's no number written right here, and the understood number is square root. But we're going to encounter later on in this lesson sometimes a different number being written there. So if there's no number written there, it's a square root. So what we're looking for underneath the radical is anything that matches another value. For example, these 5s match.
Would you just bring it out?
Yes. So what happens is that 2 5s underneath the square root is equivalent to 1 5 on the outside. So you're looking for pairs. You pair them up. 2 items underneath the square root come out as 1 item on the outside. So the 5 is now outside of the square root, but the 2, which didn't have a pair, is still underneath it. And I'd like to show you why that works, not because I'm going to ask you why it works later, but because it sort of feels a little bit funny, and there is a really good reason of why it works. So why does this work? Well, the reason it works is because if we were to take 5 square root of 2 times 5 square root of 2, and we were to sort of reconfigure what they are, right? So multiply them out, just like we were in the last section where we have 5 times 5 is 25, right? And then the square root of 2 times the square root of 2 is the square root of 4. And what's the square root of 4? 2. And then 25 times 2 would be 50, which is exactly what we had underneath the radical to start with. Okay. Why in the world, I'm going to flip back a screen, I'll come back to that one in just a second. Why in the world is the square root of 25 equal to 5? Well, it's because 5 times 5 equals 25. So why is the square root of 50 5 square root of 2? Because 5 square root of 2 times 5 square root of 2 equals 50. So it's the exact same reason, it just looks different because we still have a portion of it underneath the radical. So we're going to do the same thing now with 48. So tell me 2 numbers that multiply to give you 48. Any 2 you'd like.
8 and 6.
What? 8 and 6. Fabulous. Okay. Neither of those are primes, so we got to keep going. How can I break down 8?
4 times 2.
4 times 2, and then 4 is not prime, so it's 2, 2. So I've run out of space and I'm working to the side, but there's my 3 values. And then the 6 breaks down how? 3 and 2. So those are my 2 primes over there. So I'm going to take a step over here and I'm going to rewrite this. So let's see, I have 1, 2, 3, 4 2s. And a 3. In whatever order you like. Is that okay so far? What we're going to do then is we're going to pair things up. So there's a pair of 2's here, and there's a pair of 2's here. And anytime I have a pair, it comes out once. So this will come out one time, and this will come out one time, meaning that I had a 2 come out one time twice, right? It happened twice. And then I still had a 3 underneath the radical. And if I were to simplify what that says, it's 4 square root 3. And again, if you wanted to verify that it works, you could multiply 4 square root 3 times 4 square root of 3, and you would end up getting back to 48. And those are my only 2 examples that have just numbers. So we're changing the problem slightly. Any questions on the parts with just numbers? Okay, so what happens now when I have variables? Well, we're still going to do the number part the same way. So we're going to break down 45. So 45 is what?
5 and 9.
5 and 9. 5's prime, 9's not. 9 is?
3 and 3.
3 and 3. Wonderful. So 5, 3, and 3. It's not a very good looking 3 down there at the bottom, but that's a little bit better. All right, so over here I have a square root. I have the 5, the 3, and the 3 in whatever order you'd like. And then I have x to the 4th. So x to the 4th is actually 4 x's, right? So the factored out form of x to the 4th is x, 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 x. And I'm looking for pairs. Well, there's a pair of 3's. There's this pair of x's, and there's this pair of x's. So every pair is going to come out once. So here's a 3, here's an x, and here's an x, and there is still a 5 underneath my radical. And then instead of writing it as 3xx5, we would write it as 3x squared, square root 5. Yes, Maris?
What if it's like x to the 28 or something super high? And
Yeah.
You don't want to drop them
It's a really good question. I can't remember if I have one big enough like that later to talk about it, but there's actually a real quick and dirty way to think about this. This was x to the 4th, right? It's not a very good one for us to actually look at this way, but it is true for it. What happens is that if it's a 4 underneath as a power, then you would actually divide it by 2 for it to bring it out, because you'd be pairing them up. So like, let's say you had, like you said, 28 of them. Well, if you had 28 of them, that would be 14 pairs, wouldn't it?
Yeah.
And 28 divided by 2 is 14. Like that, they'll go hand in hand. So 28 x's underneath the radical, like x to the 28th, would be x to the 14th on the outside.
What about an odd number?
So if it's an odd number, we're going to see what happens in the next problem, because I've got an odd number here. Okay? So, and then we'll expand it to be something a little bit bigger. If I forget, remind me. All right, so 12 first. How will 12 factor?
3 and 4.
3's prime, 4's not. 4 is
2 and 2.
2 and 2. So I have the square root of 3 times 2 times 2. And then I have 3 y's. Okay? Looking for pairs of things. Well, there's a pair of 2's and there's a pair of y's. So the 2 comes out and a y comes out. The 3 is left underneath and a y is left underneath. So, in general then, anytime I have an odd number of variables, one of them still will be underneath the radical. So imagine what would happen if I thought about a bigger number like you were kind of looking at. Let's actually go with 29 just because we looked at 28 before. If you had y to the 29th and you were taking a square root of it, what would you do? Well, realistically, you know one of those y's is going to be left underneath there, right? Because it's odd. And there's 28 more of them, like this. And then you can think about the fact that the y to the 28th is pairs, right? And you can pull it out. So you could still end up pulling them out as y to the 14th. You'd just end up with a y still underneath as well. Okay? So there are definitely more than one way to think about these, to process through them. And this way of factoring it is not the only way of doing that either. There are some other ways. But it does lend itself pretty nicely to talk about variables after we've factored all of the primes.
Is that 14? Is that what you said?
Yes,
Why is it 14?
because 28 divided by 2 is 14. So 28 would be divided into pairs of 2s, and it would be 14 pairs. Yep. Any other questions? Okay, let's talk about a little bit notation-wise. Radical notation. So in general, a radical has this form. Now, the ones we have done already did not have a number where I have my letter n, right? If there's no number, I mentioned before, we have an understood 2. It's an understood square root. But that n is actually called the index. This piece, as you know, is called the radical. And the value underneath it is called a radicand. And then we'll write into the notes what I've already said out loud. When n is equal to 2, hence we'd have the square root like this of a, we often shorten this to square root of a without the 2. But any other index, right, that's not 2, is always expressly stated. It means it's going to be written down. We do this in mathematics and other areas too. Right? If I write down x, we understand that that's the same thing as 1x. Right? If I write down x, we also understand that that's the same thing as x to the power 1. Right? Those are they're not hidden, but they're not expressly stated, but they're understood to be there. For indexes, the understood index is a 2. So we're going to do the same thing on a couple more examples, but we're going to look at what happens when we have a change of index. They don't have 2s anymore. They have something else. Like this one. It's cubed, or cube root, right? I've got a 3 there. Okay, so again, the nice thing about this is that the process looks very much like what we did before. We factor it. How will 16 factor? 4 and 4. 4s each factor as 2 and 2. So I have 4 2s, and I can rewrite this as cube root of 2 times 2 times 2 times 2. That okay so far? Okay. Now, before we were looking for a group or a pair of 2 items. We were doing that because it was a square root. Say that for me real loud, Maxwell. Now we're looking for 3 items because it's a cube root. So now we just group them into sets of 3. So a grouping of 3 will bring 1 out. So I have a 2 on the outside now. Don't lose the cube root. Don't lose the index being a 3. And then I have a 2 underneath there because there was 1 2 that was not in a group of 3. Okay, the index tells you how many you need for this to actually work out. 256, that's a big number. Might want to grab a calculator. 256. What do you want to divide it by? Somebody said 16. If I divide it by 16, it's 16 and what? 16 and 16, so it's 2 16s. Well, that's kind of nice because we just looked at 16, right? 16s are 4s and 4s. It's not always so nice and pretty. And then my 4s are 2s and 2s. Now, you might be thinking, well, where did the 16 come from? Well, you might remember some of your squares. Sometimes, late elementary, early middle school, some teacher will have you memorize the perfect squares. They'll memorize, right, you go 9, 16, 25, 36, that's fine. But even so, you might not have gotten up to 16 squared. If you didn't know it was 16 times 16, you could simply just divide it by 2 and go from there too. You'll get the same numbers of 2's here at the bottom. So over here now, I've got, it's fifth root. How many 2's do I have in there? 8. 1, 2, 3, 4, 5, 6, 7, and 8. And how big of groups am I looking for? 5. So I need 5 of them. And this time I end up having 3 left over, right? That's okay. So 5 of them brings 1 out. It's always one group brings 1 out. So I've got 1 out on the outside. I've got a fifth root here. And then let's actually multiply these back together. What's 2 times 2 times 2? 8. So this is 2 fifth root of 8. Any questions on that? All right, let's talk about what like terms are. Like terms are 2 terms or more, they could be more, involving radicals that are like terms if they have the same index and the same radicand. Same index, same radicand. So remember, index is the small number inside of the little corner of the root. The radicand is the value underneath the root. So if they have both those matching, then they are like terms. So if you take a look at number 7, why are 6 square root of 3 and 2 square root of 3 like terms? What makes them like terms? The indexes are both 2, right? It's a square root, and the radicands are both 3. So these are like terms, which means we can add and subtract them. So what do you suppose that 6 square root of 3 minus 2 square root of 3 would be?
4.
Right, we would simply subtract their coefficients. 6 minus 2 is 4. So I have 4 square root of 3 left over. So the square root of 3 is kind of acting like a variable would, right? If this said 6x minus 2x, you guys would probably know that that's 4x. You wouldn't try and disappear the x or anything like that, right? It would be 4x. It's the same way for radicals. Okay, the radicals match. I have 6 square root of 3 minus 2 square root of 3. That is the same as 4 square root of 3. All right, what about on number 8? Do the radicals match? They don't. And since they don't match, at least not right now, we can't do any kind of operations that combine them together. However, that doesn't mean they might not match if we cleaned them up and simplified them. So we've got to check and see if that's possible. So we'll take this 18 and we'll factor it. How does 18 factor?
6 and 3.
Okay, 6 and 3. And 6 is 3 and 2, right. So I have 2 square root of 3 times 3 times 2. Okay, and I'm going to pause on that. We'll come back to that in a minute. Let's do the same thing with the 27 now.
9 and 3.
9 and 3. And 9 is 3 and 3. So then I've got plus the 8. And then I have the square root of 3 times 3 times 3. Okay, so all I've done in that step is simply factor the radicands. Okay? What size groups am I looking for?
2.
Groups of size 2. So on this one, there's a group of size 2 here. And there's a group of size 2 in the second one as well. Okay, now we haven't had the opportunity to talk about what happens when the number comes out and there's already a number there to begin with. What do you think might happen? Yeah, you're going to multiply them. So the 2 that's already on the outside here, I'm going to actually write it down. It's going to get multiplied by the 3 I'm bringing out, and there's still going to be a 2 underneath. If you don't need to show the multiplication step to remember that, that's fine. That will end up giving me 6 square root of 2. On the other one, this 8 will end up being multiplied by the 3 that came out, with a square root of 3 still under, or 3 still underneath the square root, and that's 24 square root of 3. Okay, so these are simplified forms now. Can't simplify any further on square root of 3, can't simplify any more on square root of 2, but they're not like terms. What fails? The radicands do not match. One's a 2 and one's a 3. What that tells you is that you're done at this point. It's simplified as far as you can go. So it doesn't always mush into one single expression. Sometimes there's still 2 terms when we are actually done. All right, product rule. There's a product rule for radicands that's actually very intuitive. It's sort of like, oh, well, if I were guessing what it would be, it probably would look like that. It's always nice when that works out in mathematics. It doesn't always happen that way, but it's really nice when it does. The product rule for radicals says that if I have the square or the nth root of a times the nth root of b, this is the same as the nth root of a times b. Notice this is a product rule. It happens when they're multiplied. This does not work if it's added. Only if it's multiplied. Okay? So let's do an example where we're going to need it. Square root of 3 times square root of 5. Well, that would be close. Square root of 15, yeah. Still underneath the radical. Okay, so I'm going to put them both underneath the radical together. Like I said, it's like what we would want to happen, right? It's what we would sort of expect should work, and it does. Okay, it will work as well for the next one. 6 times 15. Now, it's perfectly fine if you really want to multiply 6 and 15, but I'll tell you right now that's sort of counterproductive. Because the goal, after we do so, is going to be to factor it back out. Are you with me? Well, 6 times 15 is already factored somewhat, right? So it would probably be more helpful not to multiply them together, but to continue factoring them out. So yes, put them underneath the same radical, but let's actually factor to continue. So 6 is 2 and 3. 15 is 3 and 5. So this is the same as 2 times 3 times 3 times 5. Okay, so let's say you forgot and you actually multiplied the 6 and the 15 together. That's fine. After you do it, you're just going to have to factor it, and then you're going to break it down and do the same thing. Okay, so it's not going to lead you astray. It's just going to end up with one more step that you've done that you didn't really have to do. How many am I going to put into a group here? 2, because it's a square root. So the 3 comes out. I have a 2 and a 5 left underneath the radical, which means what's underneath my radical? 10. So this is 3 square root of 10. Okay, you guys good? Okay. The third one you can see has an actual variable in it, right? So that's good stuff. A little change it up. So the 5 and the 2 is 10 still. And then I have z squared, or I can write z times z. I mean, 5 times 2 is 10. That's not going to create any pairs, right? That's why I went ahead and just multiplied them together. Kind of like at the very first one here, the 3 and the 5 making 15. That doesn't create any pairs, so we just multiply it together. But the z's are pairs, right? So the z can come out. And I have square root of 10 still underneath. Any questions on that one? Okay, 12. 12 looks a little different. What do you see happening on 12 and 13?
Distribution, addition.
Yeah. I have multiplication and I have addition and I have parentheses around the addition. We've talked about the distributive property already. And the distributive property holds here as well. So the first thing I'm going to do is to simply rewrite this. This is square root of 7 times square root of 5 plus square root of 7 times square root of 7. The product rule says that I can put the 7 and the 5 underneath the radical, the 7 and the 7 underneath this radical. Well, the first one, 7 and 5, they don't break down and they don't pair up, right? Yeah, so it's just square root of 35. But square root of 7 with both the 7s underneath there, those pair up. So there's a couple different ways you can think about that. One way you can think about that in terms of the pairing up is that the 7 comes out and there isn't anything left underneath the radical for us to need to write a radical anymore. So that's one way of sort of thinking about it. The other way of thinking about it is to recognize that this is square root of 49, right? And what is the square root of 49? 7. Okay, so that's another option. Both of them will yield the same number, 7.
Is that it?
That's it. Yeah, there's nothing we can do to combine those two together. So it's okay for one of them to end up in radical form and one of them not to end up in radical form. Yes, ma'am.
Why didn't we add 5 and 7 versus and then multiply that?
Okay, so we do not have a property that allows us to add values that are different radicands. That's why. Yeah, so order of operations would say if we could have added them, we would have. So like if they both said square root of 5, then we could have, but they didn't on this particular one. Good observation. Same thing's happening on the next one, right? I have distribution, that is. So we're going to write it out a little bit. So I've got 2, and I've got the square root of 5 times 15. So the 2 stays on the outside because it was already on the outside. The 5 and the 15 stay underneath the radical because each of them were underneath radicals. On the other one, when I do this piece and this piece together, the 3 is not underneath a radical, right? So it gets multiplied by the 2 that is also not underneath a radical. And the part that's underneath the radical 5 still stays underneath the radical. Okay, so it's a like pieces part, right? I multiply the pieces that are in the like position. If they're both underneath the radical, they stay underneath the radical. If they're both on the outside, they stay outside. Now, the 5 and 15 is partially factored because 5 times 15, but 15 itself can be factored into 3 and 5. So I can rewrite that as 2 square root of 3. Well, there's a 5 already there. And then I've got another 3 and a 5 that we just found. And I still have my 6 square root of 5. Okay, I'm looking for pairs because it's a square root. Is there anything in pairs?
5.
Yeah, the 5s. So the 5s here are in pairs, so I'm going to bring them out. And what am I going to do with the 5 and the 2 that's on the outside already? Multiply them. So there's 10 outside here. I still have a 3 underneath. And I have a 6 square root of 5. The radicands do not match, so I cannot combine them, and I simply have to stop at that point. Okay, next piece, you ready? Jasmine says no. Well, we're going to move on anyway. Quotient rule. The quotient rule for radicals actually talks about the fact that if I have the n radical of A and the nth radical of B, that's the same thing as having the nth radical of A over B. It's the same as the product rule, right? As long as the indexes match, I can combine them underneath the radical with the same operation they were originally combined with. This time it simply is division. Last time it was multiplication. So I want to put a little note in here. You can write this like maybe at the very bottom of your page where you have a little bit more space. Consider square root of 3 over square root of 7, which is equal to square root of 3 over 7.
Oh, that's already on here, I'm pretty sure.
Is it? Is it on the next page? It is. Oh, my examples are backwards. Okay, never mind. Thank you. I got off on my notes. Okay, we'll come back to that. Let's do 2 examples and then we'll come back to it. Thank you, Maxwell.
No problem.
Okay, so we've got an example, number 14, square root of 3 over square root of 75. So the quotient rule says that I can put the square root here and I can put the 3 on the top and the 75 on bottom, like that, right? That's what the quotient rule says. And then anytime we're dealing with something with division, right, with fractions, like that, we would want to see if we have the ability to simplify them. So, do 3 and 75 have any factors in common? Yes, 3. So I can divide each of them by 3. It's 1 over 25. But 1 over 25 actually means that I have the square root of 1 over the square root of 25, right? It's the quotient rule in the reverse. What's the square root of 1? What's the square root of 25? 5. So what started out in radical form on this one ended up not having any radicals at the end. That doesn't always happen. It's not going to happen on 15. Okay, let's look at 15 then. 15 is not a specific example of the quotient rule that we've said per se, but you do see that there's division, right? I do have a quotient here. So what do I do when I don't specifically have a quotient that I can kind of combine like I did before? Well, one of the things that you might remember about fractions, it's not something that we've specifically talked about, so you might also not, is that I can actually divide them up into 2 separate fractions. So this is negative 25 over 5 and 15 square root 3 over 5. We talked about it the other way. We talked about it from the sense of, hey, I can't add anything together unless I get common denominators. So once I get common denominators, I mush it back together, right? So this is operating in reverse. It's saying if it's all mushed together, I could also separate it back apart. Okay? So what is negative 25 divided by 5? Negative 5. And then if I'm looking at the 15 square root of 3 over 5, again, I look at the parts that are alike. The 5 that's on the denominator is not underneath a radical. So if it's going to simplify with something, it has to simplify with the piece that's not underneath the radical. And it does. That's the 15. So what I'm really going to be dividing are these 2 pieces. What is 15 divided by 5?
3.
It's just 3. So I have plus 3, square root of just still the 3.
No over 5? Oh, okay.
We divided them out. Right. Okay, are you good? Makes sense? All right, now we're going to go back to what I was doing when I was trying to jump the gun. That's good because you don't have to write as much because apparently I got most of it written in there. Okay, so if you consider square root of 3 over square root of 20, or square root of 3 over square root of 7, which is equal to the square root of 3 over 7, neither of those versions of this is really simpler than the other one. Okay, another way you could say that is they both look awful. They're really not simpler. But there are times when having a radical remaining in the denominator is not desirable. So the phrase you might have remembered from high school somewhere is you never get to leave a radical in the denominator. It's not exactly a true statement all the time, but for the ones we're going to work with right now, that's going to be what we're going to look at. Is when we have a radical in the denominator, what do I do next? So what we actually do is something called rationalizing the denominator. So let me show you how we rationalize the denominator. And we'll do it with an example. Same as the one we just had, square root of 3 over square root of 7. Okay? We are going to multiply that denominator by itself. Square root of 7 is the denominator, so we're going to multiply by square root of 7. Now, this is a fraction. You can't just go multiplying what you want to wherever you want to. In order to make it equal to what it was before, if I do something to the denominator, I have to do it to the numerator. Okay, they go in tandem. They're in pairs. Okay, well, the product rule says that I can multiply what's underneath the radical now. So this is square root of 21 on top, and it's the square root of 49 on bottom.
So 7.
Right. So on the bottom, what happened is that ends up giving me a whole number and no radical anymore. And that didn't happen by chance. We made it happen. We made it happen when we multiplied the denominator by itself. Okay? So if you take a look at the next one, we could do that too. But it actually might be nicer to simplify what we have to start with before we worry about the rationalizing part. Because 3 and 24 have something in common, right? Yeah, they have 3's. So I can divide them by each other. Whoa, whoa, whoa. There we go. Or not by each other, but by 3. So 3 divided by 3 is 1. And 24 divided by 3 is 8. Okay, are you good? Okay. Property of radicals says I can do square root of 1 on top and square root of 8 on bottom. What's the square root of 1? 1. To do the square root of 8, we would have to factor. How will it factor?
2.
Yep, 2 and 4, which is 2 and 2. So this actually gives me square root of 2 times 2 times 2. This is the messiest one we've done so far, without a doubt. I'm looking for pairs, right? Because it's square roots. And I have one. So now I have 1 over, a 2 came out, and a 2 was left behind. Okay, so prior to what I said about rationalizing, this is what we would have done, and we would have stopped right here. We would have cleaned it up to the best of our ability. And again, there's really nothing wrong with this answer, except that the directions say to rationalize the denominator, and we haven't done that yet. So what do? Well, on the last problem, I had you multiply by the denominator exactly, right? What about that denominator is different than the denominator I have right now? Right, on the one I've got right now, there's a number on the outside. The first one that I did with the 7 only had the number underneath the radical, right? So while it's true on the first one that I multiplied by exactly the same denominator, what I was really doing was multiplying by the exact same radical and radicand. So when I look at this one, I really don't need to multiply by 2 square root of 2. If you do, it'll be okay. It'll clean itself up. You'll just have bigger numbers to work with and so forth. All you really need to do is to multiply by the radical radicand part. And if you do it on the bottom, you have to do it on the top. Okay, that's the only piece you have to multiply by. Again, if you forget or if you think I'm going to multiply by the whole denominator, it won't hurt anything. You'll just have a little bit more cleanup at the end to do. So on the top, I now have square root of 2. On the bottom, there's already a 2 here, and then I have square root of 2 times square root of 2. That's square root of 4. What is the square root of 4?
2.
Yep, that part's 2. So now I have 2 times 2 on the bottom, which is 4. I know every bit of your insides really wants to cancel that 2 and that 4. They're both even.
Wait,
Why?
So the answer is 2 over 4?
Nope. Square root of 2 over 4.
I thought it was, I don't even know.
Why can't I cancel the 2 and the 4 here? Because one of them's under the radical and the other one's not. All right? They are not alike, so we can't reduce them with one another. Got one more little bit. I knew that this lesson was probably going to take us the whole time today. It's going to be awfully close. So this is maybe the first time you're going to do everything in homework form. So if you're struggling, the Success Center is a great place to be. Talk to each other, all that good stuff, okay? All right, let's take a look at the last piece of information in the section. But before I do, anything else on that slide I need to clarify? Haley, are you good? Because you were the one asking not where something came from, but about the two.
I'm good.
You're good now?
Yeah.
Okay. Okay, the last piece in this section is we're going to talk about what a conjugate is. The conjugate of the number a plus square root b is a minus square root of b, and vice versa. Which means I could say the conjugate of a minus square root of b is a plus square root of b. When you multiply these together, you don't get any radicals. So I'd like to show you that that's true in general. Sorry, there's a typo on that. That one's supposed to be a minus. There we go. All right, so this is binomial multiplication. I know you've seen it before, but it's not something we've talked about this semester. All it is distribution twice, or you might remember FOIL from high school, those kinds of phrases. What I'm going to do is I'm going to multiply my a times my a, which gives me a squared. I'm going to multiply a times square root of b, negative square root of b, which gives me negative a square root of b, right? A's on the outside, b's underneath. And then I'm going to multiply the square root of b times the a to give me a square root of b. And then I'm going to multiply the square root of b times the negative square root of b, which is going to be negative square root of b squared. That's just the distribution of it out. We'll be doing these with numbers in a moment. So a squared at the beginning, but what do you see happen right here? Yeah, they're the exact same thing, but one's positive and one's negative, so they add to 0, or they cancel out, as we affectionately say. The last piece over here, what's the square root of b squared? B. And it's negative. Don't lose the sign, but we end up with minus just b. Okay, so what I'm trying to show you is not exactly what it ends up with, but that in fact it ends up with no radicals. Yeah? No radicals in the answer. So let's take a look at what happens when we try to rationalize denominators that have addition or subtraction in them. So up here, when we rationalize denominators, we simply multiplied by the radical part, right, that was in the denominator. So on the first one, it was the whole denominator square root of 7. On the second one, after we cleaned up a little bit of the factoring part of it, it was the square root of 2. But on these, we actually have addition and subtraction occurring in the denominator, okay? So whenever you see addition and subtraction occurring in the denominator, you have to multiply by the conjugate. So what is the conjugate of 5 plus square root of 3? 5 minus square root of 3. And if I do it to the denominator, I have to do it to the numerator. Now, in the numerator form, this will distribute out. I have 2 times 5 is 10. And then I have 2 times negative square root of 3, which is negative 2 square root of 3. Jasmine, how can I help?
I just can't see it.
Oh, is it too small? I can try and write a little bit bigger. Let me try and make it all just a little bit bigger for the moment. Is that better? Okay, cool. All right, on the denominator, here's the cool thing about rationalizing with conjugates. The inside term, that right here is the inside term, the square root of 3 and the 5, and the outside term, the 5 and the square root of 3 that are negative, always cancel out. Always. So if you want to write them out every time, be my guest. If you want to never write them out, be my guest. Because they're always going to add to 0. That's the whole point of using conjugates. So the part that actually remains will always be the first terms multiplied. 5 times 5 is 25. And the last terms multiplied, square root of 3 times square root of 3, which is 3. One's positive, one's negative, so it's negative. The goal was no radicals on bottom. Do we have any radicals on bottom? Nope. We need to clean up the denominator just a tiny bit. So the top is still 10 minus 2 square root of 3, which can't be combined. And the bottom is 22. Do you notice anything with all of the numbers that are not underneath radicals? They're divisible by 2. Everything's even. The 10, the 2 here, and the 22 here. So we will divide all of them by 2. Okay, again, all the numbers outside of the radicals have to have the property to do that. Okay, if 2 of them did and 1 of them didn't, we wouldn't be doing this. But all of them do on this one. So I have 5 minus, it's 1 square root of 3, or you can just write square root of 3, and it's 11 on bottom. Okay, and we're done. Because 5 and 11 and the 1 in front of the 3 don't have anything in common anymore. Okay, 19 is like same song, second verse. Exactly the same type of problem as 18 was. I need to multiply by the conjugate of the denominator. So what is the conjugate of 3 square root of 2 minus square root of 5?
Just addition.
Fabulous. The same thing with addition, 3 square root of 2 plus square root of 5. So first I'm going to multiply the 6 through. Again, it's outside the radical, so it will stay outside the radical. 6 times 3 would be 18. So 18 square root of 2. And then 6 times square root of 5, which would be 6 square root of 5. Okay, again, we chose these on purpose because the insides and the outsides are exactly the same with opposite signs, which means they always add to 0. Write them if you want, but they'll always add to 0. So also, don't write them if you don't want. So we're going to multiply the first terms together. 3 square root of 2 times 3 square root of 2. Well, 3 times 3 is 9. Square root of 2 times square root of 2 is 2. Precisely. The sign will always be negative in between these because one's positive and one's negative when we do the conjugate, right? So the other multiplication is the last two pieces together.
18 minus 5.
Right, so square root of 5 times square root of 5, which is 5. So I have 18 square root of 2 on top plus 6 square root of 5. And then on bottom I do have 18 minus 5. So what's 18 minus 5? 13. I would consider the terms on the outside, right? So the 18, the 6, and the 13.
I don't think you need simplify.
Yeah, 13 is prime. So unless the 18 and the 6 were to both divide by the 13, and they don't, we're out of luck, which means this version here is the final version. I know. This is going to be a challenging lesson for your homework, okay? Do not wait until tomorrow morning at 8 a.m. to start this assignment. Please. We'll do questions when you first get here like we always do, but we won't do an hour's worth of questions, okay? So if you have a whole bunch of questions, it's time to phone a friend or to go to the Success Center or to come see me potentially this afternoon or something like that, okay? Have a great evening. I'll see you guys tomorrow.